Assalamualaikum. We are from Group 2 and we are going to present about our topic, which is the Heteroborane. So before we start, I would like to introduce our group member, which is Nordini binti Zali, Nur Izzati binti Zaimin, Nur Anisulaika binti Zainuddin, Nur Zulaika binti Zainal, and me, Siti Noso Hafiza binti Zulkifli. So I will proceed to the slide of synthetic root of the heteroborane. So before I start, I would like to give a short introduction about heteroborane. So heteroborane contain heteroelement classified as nonmetal. The heteroatom known to form part of boron polyhedron, where the element that attach to the heteroborane can be either carbon, nitrogen, oxygen, phosphorus, arsenic, sulfur, selenium, and tellurium. So where either it can be either alone or in combination. So heteroborane is a classes of borane where at least one boron atom is replaced by another element. So basically, the element that can be attached in this heteroborane are from group 13, 14, 15, and 16. So these clusters are polyhedra and it can be classified as Closo, Nido, Arachno, Hypto, and etc. where this is the name of the structure. But the common structure is actually called Closo, Nido, and Arachno, where Closo is a complete polyhedron and Nido is polyhedron that missing one structure compared to the complete polyhedron, and Arachno is polyhedron that missing two atom compared to the complete polyhedron. So heteroborane can be classified by converting the heteroatom to a BHX group that has the same number of electrons. So now we are going to see the example of derivative from each group. So for group 13, derivative for group 13 is heteroborane that can containing aluminium, gallium, indium, and thallium. So for this, I will show you the example for the aluminium as the derivative for this heteroborane. So this decaborane will react with Me3 and AlH3 that contain this aluminium in diether to give this structure. This is the aluminium that attached to the in the heteroborane and hydrogen gas. The structure of B10H12AlH2 minus is that of B10H14 2 minus caged in, which an AlH2 plus group bridge the 9 position by replacing a hydrogen on each heteroboron. So this situation we can see from the structure, but this is actually for indium. So but we still can see this situation where this is we can replace this as aluminium that attached to the 6 and 9 boron, where it replaced the hydrogen that initially attached at the 6 and 9 boron. Okay.
We continue with the derivative with group 14, which is silicon and also carbon. Okay, the yellow highlighted is the reactant, while the orange highlighted is the product. So for the silicon, a solution of B10H14 and MEHSI and Me22 was heated at reflux to form 6,9Me2NH, 2B10H12 and 1,2-dimethyl, 1,2-disilica dodecarbobarane, which is the first distiller borane. And for carbon, the latter carborane, usually called orthocarborane, is prepared in good yield by the reaction of acetylene and one of 6,9L2B10H12 species, which is the L is the Lewis species. Next, for metacarborane and also paracarborane, basically obtained by the thermal isomerization of 1,12C2B10H12. For derivative with group 15, nitrogen azaborane preparation involves thermal dehydrogenation of arachno B9H3 and H2R to form the Nido B9HN and R43. The Nido compound was treated with excess Me2SBH3 at 170 degrees in the saline to form Closo, BU, HN, and R. Next, we have derivative with group 16, which is tellurium Te. The synthesis of telluroborane B10H12Te by the reaction of PdC2 PR3 okay, basically R3 refer to pH3 MEPH2 or Me2pH with 7TeB10HN in THF at room temperature. For sulfur, the thiaborane are the most intensely developed class of heteroborane after the carborane. The thiaborane of Arachno 6Sb9H12 and Nido Sb6H11 can be converted into 1Sb9H9 which has non-icosahedral fragment structure. So basically,
Now I will proceed the presentation with the structure and name of the compounds. Heteroboranes are classes of boron hydrides where at least one boron atom is replaced by another element. The neutral boron hydrides are termed as boranes, which had been covered by the first group. For more complex polyboranes, the number of boron atoms is indicated by the common prefixes di, tri, tetra, etc. And the number of hydrogen, which is the substituents, is given by a numeral in parentheses following the name. For example, we have B5H11, which is called as pentaborane. Penta refer to 5 boron atoms and 11 refer to 11 hydrogen atoms. Another example, we have B10H12I2, which is called as diiododecarborane. Diiodo refer to 2 iodine atoms, decarborane refer to 10 boron atoms, and 14 in the parentheses refer to hydrogen and iodine as our substituents. 12 hydrogen plus 2 iodines equal to 14 substituents. Heteroboranes possess polyhedral structure, which have both closed and open skeletons. Closed polyhedra having only triangular faces, which are termed as Closo, and open structures are designated as the Nido, Arachno, and Hypho. From this figure, you can see the classifications of heteroboranes as Closo, Nido, and Arachno. On the left side, you can see the structures of Closo heteroboranes, which is a completely closed polyhedral structure. In the middle, we have Nido heteroboranes, and on the right side, we have Arachno heteroboranes. How we can classify heteroboranes with these three types of structure is by calculate the electron counts according to William Wade rules. Clusters that have n vertices and 2n plus 2 or n plus 1 electron pairs involved in cage bonding will have a completely closed polyhedral structure, referred to closoboranes. The structures is on the left side. They have general formula of BnHn2-. Clusters that have n vertices and 2n plus 4 or n plus 2 electron pairs are referred to nidoboranes. They have general formula of BnHn4-. Clusters that have n vertices and 2n plus 6 or n plus 3 electron pairs are referred to arachnoboranes. They have general formula of BnHn6-. Examples, the complete names for B5H11 is arachnopentaborane, B10H14 is nidodecarborane, 1,2-PCB10H11 is 1-phosphor-2-carbaclosodecarborane. How we can classify heteroboranes, either it is arachno, nido, or closo, will be explained after this. When a boron atom of a borane is replaced by a hetero element, the compounds are called carboranes, phosphoboranes, thiaboranes, azaboranes, etc., depending on the hetero element names. Heteroboranes can be classified by converting the heteroatom to a BHX group. How we can classify the heteroboranes is shown in a video that I found in YouTube. He showed how to classify heteroboranes by converting the heteroatom and the calculations of electron pairs of heteroboranes.
Other heteroatom can be present in boranes. So if we have group 14 atoms or elements like carbon, silicon, germanium, tin, we can replace them with BH unit because they are electronically equivalent. If we have group 15 like nitrogen, phosphorus, arsenic, we will replace them with a BH2 unit. If we have group 16 element like sulfur or selenium, we will replace them with a BH3 unit. By applying this process, we will convert the heteroboranes into a normal borane and then we will apply Wade's rule to solve the problems. So now we have to solve the following problem by replacing the heteroatoms with the suitable BH unit and then applying Wade's rule. So let us start number 1 is B9H11. Sulfur is a group 16 element, so it will be replaced by a BH3 unit. So it will be B10H14. We will separate the BH unit. Each BH unit will contribute 2 electrons. Each additional hydrogen will contribute 4 electrons, so it will be 24. That is 12 pair. There are 10 vertices, so it can be written as 10 plus 2, that is n plus 2. So it will be a Nido. So the heteroborane is a Nidoborane. It is a Nido heteroborane. Similarly, we can try the number 2. CpB10H11. Carbon is a group 14 element. So it will be replaced by BH unit. Phosphorus is a group 15 element. So it will be replaced by BH2 unit. And the rest will be similar. So it will be B12H14. We will separate BH unit. Each BH unit will contribute 2 electrons. Each additional hydrogen will contribute 1 electron. So it will be 26, that is 13 pair. 13 means 12 plus 1 because there are 12 number of vertices. So it will be a Closo as it matches the formula n plus 1. So the heteroborane is a Closo one. So this is the process for solving or determining the structure of heteroboranes. That is 3 is your homework. You can solve and give the answer in comment section. After one day I will provide the answer of all the problems.
Okay, from the video, let's see how we calculate the electron for these examples. Let's take a look first for this B5H11. We separate the formula with BH units. We have BH5, H6. Each BH unit contributes 2 electrons times by 5 plus hydrogen contributes 6 electrons, give a total of 16. From this, you can see that the formula is 2n plus 6. N is the number of BH units. As I explained before, classes that have 2n plus 6 electron pairs are referred to Arachno pentaborane. Next, we see B10H14. First, we separate the formula with BH units. BH10, H4. Each BH unit contributes 2 electrons multiplied by 10, which is the number of BH units, plus 4 electrons contributed by the hydrogen atoms. give a total of 24 electrons. From this, you can see that the formula is 2n plus 4. N is the number of pH units. 2n plus 4 referred to Nido decarborane. Lastly, we see the PCB10H11. P is replaced by pH2. C, carbon, is replaced by pH. pH2 plus pH plus B10H11, we will get B12H14. Then we separate the formula with pH units. BH12H2. Each pH units contributes 2 electrons multiplied by 12 pH units plus 2 electrons contributed by the hydrogen atoms, give a total of 26. From this, you can see that the formula is 2n plus 2. N is the number of pH units. This refers to Closo boranes. That's all from me. Next, we will continue with the bonding in heteroboranes.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Izzati binti Sahimin. So today I will continue the presentation with the bonding in heteroborane. So there are two types of bonding found out in heteroborane, which are multiple bonding and classical bonding. In multiple bonding, we can divide it into two: 3-center 2-electron bonding and 4-center 2-electron bonding. While in classical bonding, there is only one type, which is 2-center 2-electron bonding. 2-center 2-electron bonding means the chemical bond in which 2 electrons are shared between 2 atoms. So this type of bonds are very common. The next one is 3-center 2-electron bonding, which is 2 electrons are shared between 3 atoms. So this type of bonds are found in case of electron deficient molecules such as borane. And the third one is 4-center 2-electron bonding, which shows 2 electrons are shared between 4 atoms. And this type of bonding increases with the size of the cluster. So here are some examples of the structure of that contains the bonding. In structure A, B, C, D, E, and also H here, you can see that these 2 atoms are connected together with 2 electrons. So this shows the classical 2-center 2-electron bonding. So based on the color coding, also you can see that the dark blue or purple stated that it is a classical 2-center 2-electron bonding. So we've moved on with the multi-center 3-center 2-electron bonding, as we can see in the structure structure D, E, F, G, and also H. So as you can see here, the 3-center here connected with 2-electron bonding. So this structure of E, 3-center 1, 2, 3 connected with 2 electron. So the last one is the multi-center 4-center 2-electron bonding, as you can see in the structure F with the color coding of yellow. You can see here 1, 2, 3, 4 atoms or 4 center are connected with 2 electron. So that's all from me. Continue with the next presenter. Thank you.
Okay, I will proceed with the reactivity of the heteroboranes. So, as we know, heteroboranes contain heteroelements classified as nonmetal. For example, carbon, nitrogen, oxygen, silicon, phosphorus, arsenic, sulfur, selenium, and also antimony. But extensive chemistry has emerged only the azaboranes and the thiaboranes. So, in this part, I want to focus on the azaborane, which is it is also the family of the heteroboranes, in which it has the vertices that are replaced by the nitrogen or NR, which is the R, can be H or the organic substituent. For example, Closo and B9H10. So these are basically the structure of the azaborane, with the blue one is indicate the N group. Okay, so for the reactivity of the azaboranes, it can undergo mustard acid or base reactions. So for the closest species of this azaborane, which is the RNB9H9 and RNB11H11, they are stable when dissolved in the strong acids, for example, triflic acid. So how does this these species of the azaborane form? Basically, they are formed from the nitrogen bond protons of their parent molecule, which is the NB9H10 and NB11H12, that can be easily removed by base to give the anion NB9H9 negative and NB11H11 negative. So this anion can be easily alkylated by the Ri, or we can choose, for example, a metal iodide and this triflate compound to give the RNB9H9 and RNB11H11, which is the closest species of the azaboranes. And also we have the Nido cluster of this azaborane, which is the NB10H13, that can be deprotonated by the hydride base. So basically the protons are removed from the bridging position and not from the NH group. So the corresponding ion would be NB10H12 negative. Okay, so for the redox reaction, the N-alkyl derivative of this species of azaborane, which is the RNB9H9 and RNB11H11s, are stable towards iodines and bromines. Even the RNB11H11s can be dissolved in the liquid chlorines. So the mixture of the RNB11H11 and the mixture of the liquid chlorine can be kept at lower temperature, but also can undergo a spontaneous Frieden reactions. And for the electrophilic substitution, we know that the heteroboranes can undergo the electrophilic substitution. So for this Closo cluster of this azaborane, which is the RNB9H9, which is R is the para benzyl chloride, and the RNB11H11, which is the R is a metal, will react neither with the triflic acid um, nor with the metal triflates. So the mixture of one of the cluster with the metal triflates as the solvent and triflic acid as a catalyst can result in the 5 and 6-fold methylations, as we can see in this equation, which is the direction of this azaborane, which is with the metal triflates. It will undergo the electrophilic substitution, as we can see the metal here is substituted into this azaboranes, as well as with this RN11H11s. So that's it from us. Thank you for listening.